Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the classification of elements and the periodicity in their properties. The title of our talk is Classification of Elements and Periodicity in Properties, and we'll be covering how elements are organized and how their properties repeat periodically. So, let's dive in and discover the fascinating patterns and systems that help us understand the building blocks of matter. Welcome to Chapter 3. In this chapter, we'll dive into the core concepts that build on what we've discussed so far. I want to highlight the key points thoroughly, but in a way that's easy to follow. Think of this as connecting the dots to see the bigger picture. We'll explore how these ideas relate to the overall theme of the presentation, emphasizing their importance and relevance. My goal is to make these concepts clear and engaging, so you can see how they fit into the broader context of what we're working towards. Let's get started and keep the flow natural and conversational. Let's look at how elements were initially arranged. They were placed in increasing order of their atomic weights. An interesting observation was that every eighth element had properties similar to the first one. It's a pattern similar to music, where every eighth note resembles the first in an octave. This idea was called Newland's law of octaves. However, this pattern seemed to hold true only up to calcium, after which it started to break down. Now, moving on to the law of triads, which was another way to organize elements. According to this law, elements could be grouped into sets of 3, called triads. These triads were also arranged in increasing order of their atomic masses. Let's recall and revise these concepts. The law of octaves was an early attempt to find periodicity in elements, and the law of triads provided a different, more structured grouping. Both were steps toward understanding the periodic relationships among elements, which eventually led to the development of the periodic table. Let's take a closer look at the periodic law and what it revealed about the elements. It showed us important similarities among the 94 naturally occurring elements. Interestingly, even some elements like neptunium and plutonium, which are man-made, are found in pitchblende, an ore of uranium. Now, the periodic table is organized into horizontal rows called periods and vertical columns known as groups or families. The modern version of the periodic table was discovered by Henry Moseley, so sometimes it's called Moseley's periodic table. The key idea here is that the physical and chemical properties of elements follow a periodic pattern based on their atomic numbers. According to the modern periodic law, as we move across the table, the properties repeat periodically with increasing atomic numbers. Mendeleev, who created an earlier version, left gaps in his table under silicon and aluminum. He called these eka-silicon and eka-aluminum, meaning one atom below silicon and aluminum. Later, scientists found that eka-aluminum had properties similar to gallium, and eka-silicon resembled germanium. Mendeleev arranged the elements in order of increasing atomic weights, placing those with similar properties in the same vertical column or group. This arrangement was fundamental because it reflected the periodic nature of element properties, which depend on atomic weight and, as we now know, atomic number. So, in summary, Mendeleev's periodic law states that the properties of elements are a periodic function of their atomic weights, and the modern law refines this idea, emphasizing the importance of atomic numbers. This understanding is a crucial foundation for how we classify and predict element behavior today. Let's move on to Slide 5, where we explore the division of the periodic table into different blocks. First, we have the F block, which includes the elements in which the F orbital is completely filled. These are called the F block elements, also known as the inner transition metals. They generally have an electronic configuration of Ns2, N1D0-1, and N2, F1-10. Inner transition metals are typically radioactive and are characterized by incomplete d orbital configurations in both their normal and oxidation states. Next, the F block elements are often referred to as transition metals because they sit between metals and nonmetals in the table, and they display some characteristic features, such as paramagnetism and catalytic properties. Moving on, the d block comprises elements where the d orbitals are fully filled, with a general electronic configuration of N1, D1-10, and NS1-2. These are the D-block elements, also called transition metals as well, because of their unique properties. Then we have the P-block, which includes elements from group 13 to 18. These are called the main group or representative elements. Their outermost electrons range from Ns2 to Ns2P1 to Ns2P6, depending on the period. At the end of each period, you find a noble gas with a closed shell configuration of Ns2P6, making it very stable and less reactive. The noble gases are chemically inert because their orbitals are fully filled, making it very difficult to add or remove electrons. Just before the noble gases, there are two important nonmetal groups, the halogens in group 17 and the chalcogens in group 16. These groups tend to gain electrons easily to attain a noble gas configuration due to their high negative electron gain enthalpies. Finally, the S block contains elements of group 1 and group 2, which have outermost electronic configurations of Ns1 and Ns2, respectively. These are the alkali metals and alkaline earth metals. They're quite reactive, with low ionization energies, and they tend to lose their outer electrons easily to form positive ions. Their reactivity and metallic character increase as you move down the group, and because of their high reactivity, they are never found in pure form in nature. Most of their compounds are ionic, except for some like lithium and beryllium. To sum up, the periodic table is divided into these four main blocks: S, P, D, and F, each with distinctive electronic configurations and chemical behaviors, helping us understand the periodic trends and properties of elements more clearly. Today, we are going to explore some important physical properties that help us understand chemical reactivity better. These properties include oxidation states, electron gain enthalpy, electronegativity, ionic radius, ionization enthalpy, and atomic radius. Each of these factors plays a crucial role in determining how elements behave in chemical reactions. First, let's talk about oxidation states. They tell us about the degree of oxidation of an element in a compound, which is fundamental in understanding redox reactions. Moving on, electron gain enthalpy measures how much energy is released when an atom gains an electron. This property is closely related to how easily an atom can accept electrons, impacting reactivity. Next, electronegativity indicates how strongly an atom attracts electrons towards itself in a bond. Higher electronegativity usually means a greater tendency to attract electrons, influencing bond formation and chemical behavior. Then we have ionic radius, which is the size of an ion. This property affects how ions interact with each other and with molecules in a compound. Ionic radius is connected to the concept of atomic size, but considers the charge on the ion as well. Following that, ionization enthalpy refers to the energy required to remove an electron from a neutral atom. This property is a key indicator of how easily an atom can form positive ions, which is vital in many chemical processes. Finally, atomic radius is the distance from the nucleus to the outermost electrons. It gives us a sense of the size of an atom and influences many of the other properties we've discussed. Throughout this presentation, we'll see how these properties interconnect and help us understand the trends in physical properties across the periodic table, ultimately shedding light on chemical reactivity itself. Let's talk about atomic size, which is a fundamental concept in understanding the periodic table. Generally, we see that the atomic size decreases across a period, especially in the second period. This is because, as you move from left to right, the outer electrons are in the same valence shell, but the number of protons in the nucleus increases. This increase in protons leads to a stronger attraction between the nucleus and the electrons, which pulls the electrons closer, resulting in a smaller atomic radius. So, even though the number of electrons is increasing, the additional positive charge in the nucleus causes the electrons to be pulled in more tightly. Now, it's important to note that the atomic radius also depends on the principal quantum number, which determines the energy level or shell. As you go down a group, The atomic radius increases because new shells are added, making the atom larger. To connect this to the overall theme, understanding how atomic size varies helps us grasp the periodic trends and the underlying forces shaping the element's properties. It's a key piece of the puzzle in understanding chemical behavior and periodicity. Now, let's take a closer look at how the atomic size varies in relation to alkali metals. As we move down the group, you'll notice that the atomic size increases significantly. This is mainly because additional electron shells are being added, which makes the atoms larger. Alkali metals are known for having relatively large atomic radii compared to other elements. This trend is important because it influences the physical and chemical properties of these elements, such as their reactivity and how they interact with other substances. The increase in size also correlates with a decrease in ionization energy, making it easier for these atoms to lose electrons and form positive ions. Understanding this variation helps us see the bigger picture of periodic trends and how atomic structure impacts element behavior. So, as we observe the pattern of atomic size in alkali metals, it reinforces the idea that atomic structure plays a crucial role in defining an element's properties and its place within the periodic table. When we talk about ions forming from atoms, the key idea is that removing an electron creates a cation, which is positively charged, while gaining an electron results in an anion, which is negatively charged. Now, a cation is always smaller than its original atom because losing an electron reduces electron-electron repulsion and allows the remaining electrons to be pulled closer to the nucleus. Conversely, an anion is larger than its parent atom because adding an electron increases electron-electron repulsion, causing the electron cloud to expand. An interesting concept here is isoelectronic species. These are different species that share the same number of electrons, the same valence electron count, and similar structures, regardless of the elements involved. Think of them as different species that have the same electronic blueprint. Now, when comparing cations with different charges, the one with the greater positive charge will have a smaller radius. Why? Because the stronger positive charge pulls the electrons more tightly toward the nucleus. On the flip side, a more negatively charged anion will have a larger radius because the increased negative charge causes more electron-electron repulsion, which outweighs the attractive force of the nucleus, leading to an expanded size. All these concepts about ionic radius tie back into the overall theme of how atomic structure and electron interactions influence the size and behavior of ions. Understanding these differences helps us predict how ions will behave in different chemical environments. Energy is always required to remove electrons from an atom, so ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first because it becomes more difficult to remove an electron from a positively charged ion compared to a neutral atom. Similarly, the third ionization enthalpy will be higher than the second, and this trend continues. When we talk about ionization enthalpy, without any qualification, we generally mean the first ionization enthalpy. We observe maximum values at the noble gases, which have closed electron shells and very stable electron configurations. Conversely, the minima occur at alkali metals, which have low ionization enthalpies and are highly reactive. A useful way to understand this concept is that ionization enthalpy provides a quantitative measure of how easily an element can lose an electron. It's the energy required to remove an electron from an isolated gaseous atom in its ground state. For example, the first ionization enthalpy is the energy change when G becomes X plus G plus an electron. This value is expressed in kilojoules per mole. Similarly, the second ionization enthalpy is the energy needed to remove the second loosely bound electron, which is from X plus G to X2 plus G plus an electron. In this way, the second ionization enthalpy is always higher than the first, and this pattern continues for subsequent electrons. So, understanding ionization enthalpy helps us grasp how atoms behave chemically, how likely they are to lose electrons and form positive ions, which is fundamental to their reactivity and their place in the periodic table. Let's explore how electrons interact with the nucleus and with each other. There are two main forces at play here. First, the attraction of electrons towards the nucleus, which is driven by the positive charge of the nucleus, and second, the repulsion between electrons themselves. Now, because of this interplay, the effective nuclear charge that a valence electron experiences is actually less than the total positive charge of the nucleus. This reduction happens because of what we call shielding or screening, where the core electrons in the inner shells act as a kind of barrier, reducing the pull that the nucleus has on the outer electrons. Now, this shielding effect influences properties like ionization energy and atomic radius. For example, in the same subshell, like the p electrons, the s electrons can shield the p electrons from the full effect of the nucleus. Since p electrons are farther away from the nucleus than s electrons, they don't feel the full positive charge. In multi-electron atoms, this becomes even more significant because the electrons in the outermost shell aren't experiencing the full positive charge of the nucleus. Instead, they're partially shielded by the inner electrons, which leads to a reduction in the attractive force they feel. This is what we call the shielding effect, a crucial concept in understanding atomic structure and behavior. It explains why electrons in larger atoms are held less tightly and why atomic radii tend to increase down a group in the periodic table, where more inner shells are added, enhancing the shielding. So, in essence, shielding helps us understand the balance of forces within atoms and how they influence atomic properties and trends across the periodic table. Let's start by understanding why oxygen has a smaller first ionization enthalpy compared to nitrogen. The key reason lies in how the electrons are arranged. In nitrogen, the three 2p electrons occupy different atomic orbitals following Hund's rule, which means they are all unpaired and spread out. This makes it a bit more difficult to remove one because they are all equally attracted to the nucleus. In oxygen, however, two of the four 2p electrons must share the same orbital, leading to increased electron-electron repulsion. This repulsion weakens the hold of the nucleus on that electron, making it easier to remove the fourth electron compared to removing any of the three 2p electrons in nitrogen. So overall, the ionization energy of oxygen is less than that of nitrogen. Now, relating this to boron and beryllium, we see a similar pattern. It's easier to remove a 2p electron from boron than a 2s electron from beryllium. Even though boron has a greater nuclear charge, its 2p electrons are more shielded because 2p electrons penetrate less to the nucleus than 2s electrons do. The 2s electrons in beryllium are held more tightly since they penetrate closer to the nucleus and experience less shielding. This means that removing a 2p electron from boron requires less energy than removing a 2s electron from beryllium, despite the difference in nuclear charge. As we move down a group, the outermost electrons are farther from the nucleus and experience more shielding from inner electrons. This increased shielding outweighs the effect of the increasing nuclear charge, so it becomes easier to remove electrons as we go down the group. Crossing a period from lithium to fluorine, we add electrons to the same principal quantum level. In this case, the shielding effect doesn't increase significantly because the inner core electrons remain the same. Instead, the nuclear attraction on the outer electrons increases due to the higher nuclear charge. That's why ionization enthalpy increases across a period. The outer electrons are held more tightly. Focusing on lithium, its 2s electron is shielded by the inner one's electrons. This shielding reduces the effective nuclear charge felt by that valence electron, making it easier to remove. Shielding is most effective when the inner orbitals are fully filled, which is why alkali metals, with their single outermost electron and noble gas core, show this behavior consistently. Finally, I want to highlight some anomalies that can occur in these trends, but the core concepts to remember are how electron arrangement, shielding, and nuclear charge influence ionization enthalpy across groups and periods. These principles help us understand the subtle variations and why some elements deviate slightly from the general patterns. The chemistry of actinoids is quite complex, and one of the main reasons for this is that they exhibit a large number of oxidation states. This variability makes their chemistry richer, but also more complicated to understand. Unlike many other elements, actinoids can exist in multiple oxidation states, which influences their chemical behavior significantly. Now, you might wonder why some elements like zinc, palladium, and cadmium are not considered transition elements, even though they have d orbitals. The key point here is that these elements have incompletely filled d orbitals in their ground state, but their chemistry doesn't typically involve the variable oxidation states characteristic of transition metals. Instead, their d orbitals are filled or nearly filled, so they don't show the same kind of variable oxidation states, and that's why they are classified differently. Moving on, you might notice that lanthanides and actinides are placed separately at the bottom of the periodic table. The reason for this is mainly for convenience and for systematic study. These elements have similar properties within their groups, but their placement at the bottom helps us keep the structure of the periodic table clear and organized. It allows us to group elements with similar properties together visually, making it easier to study their chemistry and understand their relationships with other elements. So, in essence, separating these series helps maintain the logical and systematic structure of the periodic table, which is crucial for understanding the complex chemistry of these elements. As a general rule, electron gain enthalpy tends to become more negative as we move across a period in the periodic table. This is because the effective nuclear charge increases from left to right, making it easier for the atom to attract and add an extra electron. When the atom is smaller, the added electron is closer to the nucleus on average, which stabilizes the process. Conversely, as we go down a group, the atom's size increases, and the added electron is farther from the nucleus, making the electron gain enthalpy less negative. If the electron gain enthalpy is negative, it indicates that the process releases energy, meaning it's exothermic and energetically favorable. For example, the halogens in group 17 have very high negative electron gain enthalpies because they can easily attain a stable noble gas configuration by gaining an electron. On the other hand, noble gases have large positive electron gain enthalpies because adding an electron means entering the next higher principal quantum level, which results in an unstable configuration. It's also important to note that electron gain enthalpy values are most negative towards the upper right of the periodic table, just before the noble gases. Depending on the element, adding an electron can either be an endothermic or exothermic process. When an electron is added to a neutral gaseous atom to form a negative ion, the enthalpy change involved is called the electron gain enthalpy, or for example H. This value essentially measures how easily an atom can add an electron to form an anion. So, in summary, electron gain enthalpy helps us understand the tendency of an atom or element to gain electrons, which is deeply connected to their electronic structure and position in the periodic table. Let's talk about electronegativity and how it relates to metallic and nonmetallic properties. Nonmetallic elements tend to gain electrons easily, which means they have higher electronegativities. So, we can see that electronegativity is directly related to nonmetallic characteristics. Conversely, it's inversely related to metallic properties, meaning, as electronegativity increases, metallic properties tend to decrease. If we look across a period in the periodic table, electronegativity generally increases. This increase coincides with elements becoming more nonmetallic and less metallic. On the other hand, moving down a group, electronegativity decreases, and elements exhibit more metallic and less nonmetallic behavior. Now, a quick definition. Electronegativity is a qualitative measure of how strongly an atom in a compound attracts shared electrons toward itself. And among all elements, fluorine stands out with the highest electronegativity value of 4. It's the most electronegative element, which really emphasizes how strongly it pulls electrons to itself. Understanding electronegativity helps us connect atomic properties to element behavior, and it's a crucial concept when looking at chemical bonding and reactivity. Let's talk about valence, which is essentially the number of electrons in the outermost shell of an atom. This is a key concept because it helps us understand how atoms interact and bond with each other. When we say oxidation state, it's often used interchangeably with valence, but it specifically refers to the charge an atom appears to have in a compound. For example, fluorine generally has an oxidation state of -1, meaning it tends to gain 1 electron to complete its outer shell. However, in some compounds like OF2, fluorine can actually exhibit a +2 oxidation state, which might seem a bit counterintuitive at first. The oxidation state is crucial because it helps determine the oxidation number of an element within a compound. This number gives us insight into how electrons are shared or transferred during chemical reactions, tying directly into the overall theme of understanding chemical behavior at the atomic level. Let's look at the transition metals in the 3D series. The change in their atomic radii is much smaller compared to the representative elements across a period. Similarly, among the inner transition metals in the 4F series, the change is even less noticeable. This indicates a relatively stable size as we move across these series. Next, the ionization enthalpies of these metals are intermediate. They're not as low as S-block metals, but not as high as nonmetals. Because of this, they are less electropositive than group 1 and 2 metals, which explains their unique chemical behavior. Now, regarding metallic and nonmetallic character. Metallic character tends to decrease as we move from right to left across the periodic table, while nonmetallic character increases from left to right. This trend is due to the addition of electrons into various orbitals, affecting how elements interact and bond. When we consider elements at the extremes of the periodic table, they tend to form different types of oxides. For example, some form peroxides and superoxides, which can be acidic, basic, or amphoteric, meaning they can behave as either acids or bases. Metals generally form basic oxides, whereas nonmetals tend to form acidic oxides. Moving on to the p-block elements, the first member in each group shows a greater ability to form pp-pi multiple bonds, like C equals C, C identical to C, N equals N, or N identical to N. They also tend to form bonds with other second period elements, such as C equals O or C identical to N. This anomalous behavior is mainly because these first members are smaller in size, have a large charge-to-radius ratio, and high electronegativity. Additionally, they have only 4 valence orbitals, 2s and 2p, available for bonding. In contrast, the second members of these groups have 9 valence orbitals, including 3d, allowing them to expand their valence shell and form more complex bonds, like Al F63- in aluminum compounds. Finally, the diagonal relationship is an interesting concept. It describes how certain pairs of diagonally adjacent elements in the second and third periods exhibit similar chemical properties. This pattern is observed in both S and P blocks and helps explain some similarities across different groups, despite their position in the periodic table. Understanding these concepts really ties into the overall theme of periodic trends and chemical reactivity, helping us grasp why elements behave the way they do based on their position and electronic structure. This slide doesn't contain enough information. That's why we're moving to the next slide.